Muy bien, ya estamos listos ahora sí. Okay, so let's start. Well, so this is what we saw last time, this proposition. Remember that we proved this. The whole idea is you have one atlas and two listing charts that do not belong to the atlas. And you assume that each one of them is compatible with all of the charts in here, right? And then the conclusion is they must be compatible with each other, okay? So we prove this, you will later on see that it is useful in the definition of a smooth manifold. So we prove this proposition and then we define a maximal atlas on a manifold. So that means any compatible chart with all of the elements of the atlas also belongs to the atlas. So that's what it means to be a maximal atlas. Right, so this is what I have just said. If you have a chart which is compatible with every chart in the atlas, then it must belong to that atlas. And so in theory, we were able to define what is a smooth manifold. So it is a topological space with some requirements. And the whole idea is that it has a maximal atlas. This is our definition of a smooth manifold. Okay, as I mentioned yesterday, what we will do, we will basically, as we move on, this information, we will not write it down, and it will be clear what is the atlas on our manifold. Also, sometimes we say that the atlas is the differential structure on the manifold. Right? Because remember that M is a topological space. And the charts, it is what gives us the definition of something smooth. So A is sometimes called the smooth structure on M. And so this is the new result of today. We haven't seen this. We just finished the review of last class. And so this statement, more or less, it is useful in a theoretical sense. So basically you're saying if you have some atlas A, this is going to be contained in a unique maximal atlas, right? So this is what this theorem is saying. If you have M and you have some atlas, like remember that we saw yesterday for the sphere, we have an atlas with only two charts. Then there is a unique maximal atlas where that is contained. So before discussing the proof of this theorem, I want you to understand that it is very useful. For instance, remember that yesterday we saw the blue sphere. And I'm not going to write the maps, just the open sets. Remember? Well, let me not write it like that. We showed yesterday that we have an atlas here with only 2 open sets. And that's enough to make S2 into a manifold using the theorem, because you know that then A is inside a maximal atlas using the theorem. And hence, you have a manifold. Right? So we don't need to have a description of all of the shards in order to have something that it is a manifold. And I mean, this example is very clear because we only know 2 open sets, 2 shards. And then by that, we can conclude that S2 is a manifold. I don't know the entire description of this, but I know that in that maximal atlas, I have UN and US, and many more things. But that fits to give the definition of a manifold for S2. And also we saw S1, we can argue the same way. So that is the good thing about this theorem. In practice, it is very useful. The proof, we are not going to see here the proof. For the proof, just see the book. But let's discuss a little bit about the proof. It relies on this result that we proved last time. So take A in the atlas on a manifold. A is in the atlas. And you have many shards that are compatible with the shards of the atlas. What you do, you join them. You add all of the shards. And you will have an atlas because if you have any atlas and you have 2 shards that are compatible with them, then everything is compatible. So that's the way that you construct the maximal atlas. So that's how you get a maximal atlas. You have an atlas, you have some shards that are compatible with the shards of the atlas. You put them together, you have a new atlas because every shard is compatible with themselves. And by definition, that will be a maximal atlas. And then you will just have to argue the uniqueness part. So the proof is in the book, you can look it up. But I will instead focus on some examples. of manifolds. So up to this point, any questions?
So good so far.
Okay. So in order to define a manifold, it suffices to have an atlas. It doesn't have to be maximal because we will use this result. So this is like the first example of a manifold, S2 and also S1 that we covered yesterday. The other nice example, and it is very important, Euclidean space for any n. So Rn is a topological manifold of dimension n, and we would like to make Rn into a smooth manifold. In order to do that, we must define an atlas on Rn. In this case, you have a very simple atlas with only one chart. The open set is the whole space, Rn, and the map, it has to be a homeomorphism, is the identity. In that way, you have Rn and this atlas. Using this, Rn is a smooth manifold of dimension n. So this is what we call the standard smooth structure on Rn, the canonical structure. Okay, so that's one example. So this will give you examples of smooth manifolds of any dimension, R1, R2, R3, and so on. So you have many examples of manifolds, basic ones, but we have a few. Now, another example, if you have Rn, take any open subset. And I claim that that open subset is also a manifold. So take U to be M. Again, this is just the identity map. Remember that it goes into some open set in Rn. It has to be a diffeomorphism. So there you go. So any open set in Rn is a manifold of dimension n. Okay? Now, be careful here. I'm taking M to be open. So at this point so far, I'm not saying that R1 is a manifold. We know that R1 is inside R2, like the x-axis or the y-axis or any other curve. But I'm not saying that this is a manifold using this argument. It has to be an open set. Okay, let me I want to put another example here. it is very much related to the previous one. So you have a manifold, okay? The example that I want to make into a manifold, any open set. Any open set in a smooth manifold, it is also a smooth manifold, okay? In order to show that X is a manifold, we need an atlas. So, can you guess how to construct an atlas on X? I need some ideas. So I want to define
Maybe
some
taking
charts.
restrictions, like
Jesus?
restricting the charts from the original atlas.
Oh, wait, I have a low volume. Yeah, sorry, go ahead.
Like restricting the charts from the atlas.
Right,
So
right. So I make a chart here, right? So I know that this is open. And I know that this is homeomorphism to some open set. So then we need to define a chart on X. So we put U1, right? Let's make this interesting. So let's assume that the intersection is non-empty. If it's empty, I don't care. So if U intersection X is non-empty, first, why is U1 open in X?
that's the topology in X, right?
Right. So when I'm taking this, it is the induced topology. The open sets in X are the intersection of open sets in M intersection with X. So this is open in X. And then we're going to define the homeomorphism. Is this map restricted to this open set? So phi 1 is going to be a homeomorphism from U1 to some open set in Rn. So this will be a chart. So I have an open set and a homeomorphism from that open set to some open set in Rn. So I have a chart. And because A is an atlas of M, I have many charts that cover X. And now it only remains to show that those charts are compatible, but everything will follow because we have open sets. We have a smooth maps and we are restricting to open sets. They will be smooth. So that's the way that we have an atlas. We don't know if it's maximal, but at the end of the day, it would lie in some maximal atlas. So it's not only that open sets in Rn are smooth manifolds. Open sets of a manifold are also manifolds. They have the induced smooth structure and they have the same dimension. Okay? Well, so let's move on. Oh, now remember, so this is only an atlas. It's not maximal. This is maximal, right? Because I'm saying that's a manifold. The one here, I'm not saying that it is a maximal, but we don't care because it will fit in a unique maximal. So we have a manifold. Now, I would like to recall yesterday's example. We saw S1 with two atlases, one with 4 open sets and the other one with only 2, right? So the whole idea, we can argue any way we want. So in principle, on S1, I have this. So I have maybe you will think, okay, I have S1 with some maximal atlas 1 induced by this. And maybe I have S1 with some other maximal atlas that it is induced by this. However, it happens that this chart is compatible with all of them and also this one. So those two atlases lie in the same maximal atlas. Okay? So maybe. So this is what I want you to do in the homework. That they are compatible. So A okay? So in principle, we have two atlases on this one. but they will induce the same smooth structure on the circle. They lie in the same maximal atlas. Okay, so that's a homework check that they are compatible, all of these 6 charts. Oh, well, this is what we saw already, right? So I got ahead of myself, but this we already covered upstairs. It is the same example. Open sets of a manifold are manifolds. Any questions? Okay. Now, let's do something more interesting, and that will be the next example. I have 2 manifolds, M and N. Okay? And remember that M is a topological space, N is a topological space. If you do the Cartesian product, that's a topological space. Do you remember the topology?
The box topology.
Right, so this is the box topology, and there's no problem. We have a finite number, right? So when you have many of them, you have to be careful. But here, for the Cartesian product, a basis for the topology, open set cross open set. That's a basis. Okay, so this is how we construct an atlas on M cross N. M cross N is a topological space, and we would like to define an atlas in terms of the atlas of M and the atlas of N. So this is an open set in M cross N because it is the cross product of 2 open sets. This map is the homeomorphism, right? You will have a homeomorphism to an open set in Rm plus N. The shards will be compatible, okay? And because all of the U alphas cover M and all of the V betas cover N, all of this will cover M cross N. So that will give you an atlas, and that will give you a smooth structure on the Cartesian product. Okay? So now we have all of that. So now I'm done with all of the straightforward examples that we can have of manifolds. Okay, let's move on. Okay, this observation is basically the same we discussed before. So I have a manifold, I have a chart, and I'm just creating a new chart that maybe is not in A. Yeah, well, it is. So this is maximal. I take any open set, I restrict this as before. So I have in a new chart. And like for instance here, let me tell you why I make this remark here. Again, remember what you have done in analysis or in topology. Sometimes you need to have smaller open sets for any reason. And that's why it is important that for a manifold, we always talk about the maximal atlas. What I'm saying is that we have a new atlas. Because A is maximal, it will belong to A. And you can construct just take any open set in the chart. And that will give you another chart. That chart will be compatible, so it has to belong to A. So that's the whole idea that I wanted to stress here. Because A is maximal. So I just want to stress the definition of a manifold, that it is important that we have a maximal atlas. It contains all of the charts that are compatible. And this is a way to create a new chart. Take any small set inside a chart, and you will get a chart in the same atlas. V is any open set, small if you want, and that will give you a chart. Okay, so now, so far, we will put aside the concept of a manifold. A manifold is a topological space with some topological conditions, and we have a maximal atlas, right? And we saw many examples of manifolds. We are going to see more examples, okay? Here I'm just putting a break on the list of examples that we have seen of manifolds, but we will see more. But now we are going to move to some other important objects of manifolds, which are smooth functions. Okay? So I will start with a manifold, and you will see as we progress that sometimes I'm going to omit the A. So I have a manifold and a function f. I would like to define what it means for a function to be smooth. That's the whole idea, right? M is a topological space. So you know if I give you f is a continuous function on M. That's something that you know very well. But I would like to define what it means to be smooth or differentiable. So we are going to define the concept of smoothness point-wise. So we will say that f is smooth at a point if you can find a chart such that this function is smooth. It is better to have a drawing of this. Okay. So I would like to say when f is smooth at P. What this is telling me is it's going to be smooth if you can find a chart about P because P is a chart, you have a function into Rn. Okay? And then this is what I told you last time. Because now I'm looking into a function here. And that function is I go down and then I apply f. So this function, the domain is an open set in Rn. So this function is a function of multivariable calculus. And you know how to take derivatives of that function. Right? So that's why we have all of this. So in order to say that this function is smooth, I have to go up the Euclidean space and consider that function. So this is again what we discussed yesterday. So below, we don't have nothing. Above, we have Rn and we have multivariable calculus. And that's how you define the concept of a function that it is differentiable on a manifold. Right? For instance, here, remember, by the definition of a chart, this set is open. So I have a function defined on an open set in Euclidean space. So we know what it means to be smooth at a point. Okay, so that's the definition of a smooth function on a point. And if we would like to say that f is smooth on M, so we just say that it is smooth at every point of M. Right, so now we have to deal with this. The definition involves some charge. Next, we will show that it is independent of the charge. Once that you know that it is differentiable, if you take any charge, that will hold. Okay? So that's the observation that we have below. So far, the definition involves a chart, but it is independent of the chart. So take V, be any other chart. Obviously, it has to belong to the atlas, right? It has to be compatible. So we have another chart. And we have something like this, right? So this goes to some Rn. We know that this one is smooth. That's what we know. And we would like to show that this one is also smooth. Okay? These two charts are compatible. They belong to the atlas. And that's important. So let's see now. Because they are compatible, so we know that this is smooth, right? Which is this and this one. And I think we will only need that one, but let me write the other one also. No, well, let's not do that one. Okay? I want to show something like this, but with psi. I know it works with phi, but I would like to have psi. Okay, and I think I need the other one actually. Okay. Now, here I'm using the fact that the charts are compatible. I'm not being precise, but keep in mind that this function is not defined on all Rn. It is only on the image of the intersection, right? It goes here. And also the other one, the intersection only, right? Okay, now, what I said here is what I wrote here. The charts are compatible, so that function is smooth. And now we're using concept of multivariable calculus. The composition of smooth functions is smooth in Rn. And this is what we have. This function is defined on an open set in Rn. Also this one. Both of them are smooth. So this one is smooth. And that's precisely this function. So using this chart, f is smooth. Keep in mind that we're using concepts of calculus. This is smooth on an open set in Rn. Also this one. So from calculus, the composition of those two smooth functions is smooth. So I'm using the result of multivariable calculus to conclude that this new function is smooth. And that's what we were aiming at. So once that we know that it is smooth with respect to one chart, it's going to be smooth with any other chart in the atlas, any compatible chart. So this shows that this definition, it doesn't depend on the chart. If it works for one, it will work for any other chart. Okay? Great. So we just define what it means to be smooth pointwise and to be smooth on the manifold, so it is required to be smooth at every single point. And that's just the definition of a smooth function. So this is the importance of having an atlas on a manifold. Here we only have topology, but the atlas allows me to go to Euclidean space and use calculus to define a smooth function. Okay, any questions? Okay, so let's move on. I'm going to use this definition for the set of all smooth functions. So again, M is a manifold, and I'm just writing M, but we always have a maximal atlas there. So this is the set of all smooth functions. So this concept depends on the maximal atlas, okay? Because we use the charts to define a smooth function. And what you expect, so this is going to be a ring. You define the sum of two functions in the same way. You can check that it will be smooth. You can also multiply functions and they will be smooth. So I'm not going to prove that. Okay, now. So now we are going to generalize this concept, but instead of R, we will take any manifold. And say when a function between two manifolds is smooth. So I take two smooth manifolds, M and N, and I have a function between them, and I would like to define F smoothness on F, okay? So first we will define to be smooth on a point in the domain. So this P is in the domain. And maybe you can guess what is the definition. So I'm going to require now two charts, one on M, one on N, and I will require this function to be smooth. So what are we doing now? I have a point in M, P, I have f of P. In order to say that f is smooth at P, I require a chart here that I call U. I also require a chart here that I call V. This is M. And again, in order to say that something is smooth down, I require to be smooth above. So this is the function that I must consider now. That is 5 inverse F psi. This function is defined on some open set in our N. So again, my calculus, you know what it means for this function to be smooth. So this is the definition for f to be smooth on a point P. And the global concept of a smooth function, so we just say that that happens at every point of the domain. Right? Okay, I don't have it here, but this definition is independent of the charts of the atlas that we consider. If we take any other chart in the atlas of M and any other chart in the atlas of N, the same will hold. So this definition is independent of the charts. So any questions up to this point?
Nope.
Hasta el gallo está de acuerdo. Ya con eso me doy por satisfecho. Muy bien. Okay, so let's continue. Now, something that it has to puzzle you is the following. You see, I just defined a smooth function between two manifolds. I have this and I have this, right? Prior to that, we define what it means for a function like this to be smooth. But remember here, we only have something like this. We only consider one chart on M. We only did this. Well, everything makes sense because if you would like to consider this in the same way like this, it's exactly what we defined before because you take P, sorry. The definition was take a chart, U. But now here, you have f of b. The chart that you take in R is v equals R. And this, the identity. Okay? And what is this function? So, smoothness of this function in this term, when you take R to be a manifold, it is the same because here is the identity. There's nothing new. So, everything makes sense. There's no contradiction in our previous definition of real value functions. Because we were considering, we didn't write it down, but this chart in R with this function, the identity. Right, so everything works well. It doesn't matter if you take this as a manifold and use this definition as opposed to the previous one. Right? Okay, so that's the observation that you might have when you consider N to be R. The two definitions agree. There's nothing wrong going on here. Well, this is what I have. Okay, now we denote it this way, the set of all smooth functions between two manifolds. Now here we don't have any algebraic structure like before, that we have a ring. Here is only a set. The set of smooth functions between M and N. This observation is the same one that I made here. Is that your function f? Here, you take the identity. V is Rn. Again, you take the identity chart. Q is Rn. So this is inverse f, and that is f itself. So the concept of a smooth function in calculus is the same here. There's no change. We have exactly the same by using that chart, the whole space and the identity map. So is it clear what is the whole point of this observation? So smoothness from calculus, it is the same as manifolds. When Euclidean space, instead of thinking of it as in calculus, you think of Euclidean space as a manifold. It is the same concept of smoothness. Okay, now let's this observation is something that we will use later on, but it is very important. So you have a manifold and make a chart. Okay. Now U is open in M. Oh, sorry, this is wrong. So U is a manifold, right? That's what we discussed earlier. If you have a manifold, any open set is also a manifold. So this map of the chart is smooth. That's what I'm saying. So that will be something very important and useful, that the function of a chart is a smooth function. Obviously, it's not defined on all of M, only on the open set U. But that will be a smooth function on U. Okay, so that will be very useful that we have this. Before they were homeomorphism between U and some open set in Rn. But now we know that that function is a smooth function on the manifold U. Okay, now let's prove this proposition just to get used to the concepts that we have defined so far. I want to prove that the composition of two smooth functional manifolds is also smooth. Okay, so it suffices to prove that it is smooth on some point. I take an arbitrary point, and now by definition, if a function between manifolds is smooth at P, any shard on P and any shard of f of P will give me a smooth function. Let's call this B. Okay? That's just by definition of a smoothness of f at P. Similarly for the other part. G is a smooth at f of P. I already have a shard on f of P. Now I need a shard on G, f of P. So now, what is this? So it will be no, this is wrong. Okay. Now, note that this function is defined on an open set in Euclidean space. This function is also defined on an open set in Euclidean space. Moreover, the domain of this function is the image of this function. So you can compose both of them, and from calculus, the composition is smooth. This is wrong. Wait, so I wrote something wrong on this last one. What is the right function? This is incorrect. So the last one, right? This is wrong. Yeah, this has to be 50. 5 dot, which is that's the Charlotte domain. Okay, so now we compose this composition is smooth. But what is that? This is only this one. Okay. So you have B, f of B, and G, f of B. I took U and phi. Goes to some Euclidean space. And then here, I took V, and this one that goes to some Euclidean space. This is F, G. Here I took W, a chart, and phi naught. By hypothesis, F is smooth on P. That means that this function is smooth. This function is smooth at phi of P. Similarly, G is smooth at f of P. So this function defined on some Euclidean open set is smooth. The problem was to show that this is smooth. precisely this map, which is that one, right? So this is smooth by hypothesis. Also, this one is smooth by hypothesis. So this one is smooth, which is this one between open sets in Euclidean space. Right, so everything above the gray line is calculus, multivariable calculus. Smooth function defined on open set of Euclidean space. Very good. Any questions?
Nope.
So, I mean, basically what I wanted to do here, I just wanted to have an exercise that involves the concepts that we have just defined. So that's the whole idea. Okay, so let's move on because there are something important aspects that we need to consider. So a smooth map between two manifolds is called a diffeomorphism if it has an inverse and the inverse is also smooth. So in the concept of manifolds, we have a diffeomorphism. That is equivalent in topology when you have a map between topological space and you define it to be homeomorphism. A continuous map which is bijective and the inverse is also continuous. So that's in topology, and in manifolds we call it a diffeomorphism. Smooth, bijective, and the inverse is also smooth. Okay, now. And again, two manifolds are said to be diffeomorphic if you have a diffeomorphism between the two. So, something that you have done in topology, now we have it here. Okay, now this concept, which is this one also, it is very important and it is fundamental. Like, remember S1. I'm sorry, yes, S1. For S1, remember that we have two atlases. The north and south, that's an atlas. And we saw another atlas with 4 shards. So this is the example that I have here. The same manifold, but I have a different atlas. Or a different maximal atlas, if you want. Okay. What I have said is that you have the topological space, and the atlas is what we call the smooth structure on the manifold. So it may happen that you have a manifold with some atlas and the same, you have a topological space with some maximal atlas, and you have the same topological space with some other maximal atlas. So in principle, the smooth functions here are different than the smooth functions here because you don't know any information about the atlas, A1 and A2. But it can happen that they are the same manifold from the point of view of smooth manifolds. So tienen un mismo espacio topológico M y por alguna razón tienen dos atlases maximales. A lo mejor aparentemente se ven diferentes. Y no solo eso, una manera de ver de que son diferentes los atlases es si tienen una función. Que aquí es diferenciable y acá no. Entonces, de un lado sí pueden derivar, pero con el otro no la pueden derivar. Entonces, aparentemente como que son variedades diferentes. Y la manera de ver si son iguales es la existencia del difeomorfismo. Difeomorfismo como función suave involucra las cartas, ¿de acuerdo? Entonces va a involucrar esta información y esta otra. Entonces son iguales en el sentido como variedades si existe un difeomorfismo. Y les digo, esto en primera instancia puede ser el ejemplo del círculo. Vimos un atlas con dos cartas, norte y sur, y después vimos otro atlas con 4 cartas. Bien. Yo les dije porque es fácil. Vean que las dos cartas de la proyección estereográfica son compatibles con las de acá. Y entonces esos dos atlas tienen el mismo atlas maximal. Pero digamos de que aquí fue sencillo porque nada más había 2 cartas que verificar. Pero si tienen muchas más, número finito o inclusive un número infinito, compararlas a mano no es tan sencillo. Entonces, por eso es importante el concepto de tener una función entre variedades. Entonces, si encuentran una función que es un difeomorfismo, en términos de como variedad, es la misma variedad. Aunque como conjunto de atlas son diferentes. Un ejemplo de eso lo van a ver en el problema 6.3. Es ilustrativo y sobre todo porque para hacerlo todavía más ilustrativo se toma la variedad más sencilla que es R1. R1, de momento nada más hemos visto el atlas maximal que contiene la identidad. Y así es como lo consideramos a R1 como variedad. U es R1 y phi la identidad. Eso es una carta. Como ya cubre todo, eso me define un atlas. Y por lo tanto ya tengo un atlas maximal. Y así consideramos a R1. En el problema les van a dar otra carta. Y no va a ser compatible con la que yo les estoy diciendo. Pero van a ser difeomorfas. Muy bien. Entonces, por eso es importante el concepto de difeomorfismo, entre otras cosas. Pero también está esta otra pregunta que ya se pueden hacer. Digamos que tienen M, ella es una variedad. M con su atlas maximal. A M le puedo encontrar otro atlas que sea totalmente diferente al que ya tengo. De manera equivalente, puedo darle otra estructura suave totalmente distinta a la que ya tenía. Bien, esos fueron problemas que no se sabía la respuesta. Entiendo el concepto de variedad, tengo un atlas maximal. Se habían dado atlas maximales distintos, pero que eran difeomorfos. Ahí está el de la tarea. Así de que como variedad es la misma, aunque yo tenga otro atlas diferente. Pero realmente había algo que lo hiciera totalmente distinto. Ese fue un problema abierto por mucho tiempo y se resolvió hasta el 56. Ya vimos S1 y S2. En general Sn lo pueden ver con las cartas usuales de proyecciones heliográficas. En Sn le pueden dar una estructura de variedad con solo dos cartas, como lo hicimos con S1. Muy bien. Las esferas de cualquier dimensión son variedades y esa estructura que les he dicho es la estructura canónica, el estándar. Bueno, en el 56 vieron de que la 7 esfera tiene otras estructuras diferenciables que no son equivalentes a la que conocen. Y el adjetivo exótico generalmente quiere decir eso. Algo que conocemos muy bien con estructura estándar, pero se encuentra que tiene cosas adicionales. Entonces, ese fue el primer ejemplo de una variedad con dos estructuras diferenciables totalmente distintas, que no eran difeomorfas. Muy bien. No tengo la otra referencia, se me pasó ponerla. Pero, por ejemplo, a los espacios euclidianos, R1, R2, R3, Rn, ya hemos visto la estructura diferenciable estándar. Pero estaba la duda, bueno, igual como en la esfera, los espacios euclidianos pueden tener otra estructura euclidiana distinta, perdón, estructura diferenciable distinta a la que conocemos. Y ese problema permaneció sin resolver, creo que hasta los 80s. No sé muy bien, de R6 para arriba, nada más la que conocemos es válida. R2 para abajo también. Creo que R3 y R4, de R4 estoy seguro. De R4 están los R4 exóticos. Hay una estructura diferencial de variedad que no tiene nada que ver con la que usamos. Entonces, eso ya vino después en los 80s. Y les digo, de R4 estoy seguro, no recuerdo de R3. Entonces, está ese detalle que, bueno, ahora ya se entiende más, pero cuando uno estudia esto de variedades, tienes un espacio topológico, le puedes dar, en principio, distintas estructuras diferenciables. Entonces, vean este problema, es en R1. Aparentemente son dos atlases diferentes, pero son difiomorfos. Okay, any questions? Well, so let's continue with the concept of diffeomorphism, because this concept is important when we take the same manifold. M maps from M to M. Oh, well. First, this observation I forgot. If M and N are diffeomorphic, they have the same dimension. But tell me why this is true. Here you have the definition of diffeomorphism. If you have a diffeomorphism between two manifolds, why do they have the same dimension?
Isn't it like already a homomorphism as well?
Right. So it will give you a homeomorphism between open sets in Rn, in Euclidean space. And then we will have right? So you have here F, M, and N. You take some chart, some open set, and here another chart on some open set. like this. By definition of a chart, this is a homeomorphism to an open set. This is a homeomorphism. So this is homeomorphism, homeomorphism. And we are saying that F is bijective and smooth. So this function is going to be a homeomorphism between open set of Euclidean space. And remember what we discussed yesterday, so they have to have the same dimension. And remember, that's a result that we haven't proved. We only prove for n equals to 1 and n. Right, so diffeomorphic manifolds have the same dimension. And also, when we look at the same manifold, a diffeomorphism of the same manifold, I have this, that's the notation. And we prove a proposition, the composition of a smooth maps is smooth. So under the composition, this is a group. So if you have a fixed manifold, you look at the set of diffeomorphism of that manifold with itself, and that's going to be a group under the composition of maps. Okay? So if two manifolds are diffeomorphic, you will have an equivalence relation. In the same way that if two topological spaces are homeomorphic, that will give you an equivalence relation on the set of topological spaces. Right? So you have here that rectangle is the set of all manifolds. So we have the set of all manifolds. And remember yesterday, I mean, we haven't seen diffeomorphisms until today, but yesterday you told me a way that has topological manifolds, R is the same as 0, 1. Yesterday you gave me a homeomorphism. That homeomorphism is in fact a diffeomorphism. So 0, 1 and R are diffeomorphic manifolds. So you have it there, right? S1 is a manifold. For instance, maybe here you would have S7 with the atlas is the standard one. But here you have another one. We don't know what it is. How do we define the atlas? But if we just recall this, so S7 has a smooth structure and another one which is not related. So we put together all of the manifolds that are diffeomorphic among themselves. That's equivalence relation of the set of all manifolds. And so we have a partition. And in some ways, the whole idea of part of the idea of manifolds is to classify them, right? So how to decide when two manifolds are diffeomorphic or are not diffeomorphic. Entonces, el concepto de diffeomorfismo es una relación de equivalencia y no podemos distinguir entre variedades que son diffeomorfas. Entonces, todas ellas están ahí en el mismo espacio. Ahorita todavía, pero no tanto, pero todavía en los 80s estaba esta idea de clasificar o tratar de clasificar todas las variedades diferenciables. En dimensión 1 es algo que se puede hacer y es lo que tengo aquí. En dimensión 1 prácticamente es el intervalo abierto y el círculo. Son las dos únicas variedades de dimensión 1. Lo que mencioné anteriormente, el trabajo de Milnor, la esfera de 7 dimensiones tiene estructuras diferenciables que no son diffeomorfas. Pues al menos tenemos la canónica y alguna otra por ahí. También lo que dije de R4, a lo mejor aquí está R4, muy bien, y por acá está el R4 exótico. El R1 del problema que tienen de tarea, los dos están aquí. Ahí van a ver cuáles son los distintos atlases, pero son diffeomorfos. Ahí están. Igual, con conocimientos de topología, el intervalo abierto 0,1 es homeomorfo a R. La bola abierta en el espacio euclidiano es homeomorfo al espacio euclidiano. Y también como variedades. Aquí pueden tener la 4 bola abierta. Como es una abierta en Rn, con esa estructura de variedad, y es la misma variedad, no pueden diferenciar. Muy bien. Y entonces, para poder diferenciar todo esto, no es tanto de que uno se ponga a estudiar cómo son las cartas y el atlas y todo lo demás. Más bien, lo que uno ve y uno define es lo que le llaman invariantes. Definir invariantes para poder distinguir variedades. Generalmente para poderlo distinguir, algo que sea más fácil de diferenciar, como un número o un espacio vectorial, un objeto algebraico, un anillo, un grupo. Y de esa manera uno puede distinguir entre las variedades, generar invariantes. Si dos variedades son diffeomorfas, van a tener ese mismo número de su invariante. Entonces, si obtienen para dos variedades números distintos, no pueden ser diffeomorfas. Entonces, generar o construir invariantes es algo en lo que se trabaja mucho. Hoy en día no tanto, les digo, ya como que se logró todo lo que se tenía. También uno es consciente de que no va a lograr clasificar todas las variedades de dimensiones arbitrarias. Por cuestiones de que son más pequeñas las dimensiones, sí se puede. Dimensión 1, el círculo y el intervalo. Dimensión 2 también. Pero ya en mayores dimensiones no se espera tener una lista completa, pero sí tener conocimiento de ello. Muy bien. Y hasta aquí, ¿alguna duda?
No, todo bien.
Muy bien. Voy a terminar. Bueno, esto lo vamos a ver en la siguiente clase. Ya vimos cuando una función es diferenciable. Eso ya está ahí todo. La definición nos dice de que si existe una carta con estas propiedades. Después vimos que si es diferenciable, no importa qué carta nos tomemos. Es independiente de la carta. Y bueno, ahora lo que vamos a hablar es un poco de derivadas parciales. Pero pues eso lo veremos la siguiente clase. Muy bien. Entonces, ¿preguntas? ¿Dudas? Perfecto. También para la siguiente clase les voy a pedir no sé si lo vamos a usar la siguiente clase o dentro de una semana. Recuerden, en varias variables y también en una variable, el teorema de la función implícita. ¿De acuerdo? Recuerden esa parte para que lo vamos a necesitar aquí. Muy bien.
Ok. Profe,
Bueno,
¿los problemas se los mandamos por algún lado?
ajá, los que les dejo en la clase tal cual, no, es nada más para que los hagan. No estoy pidiendo que me los entreguen. Cuando ya en Classroom les ponga los problemas para entregar y todo, ahí sí, Jesús. Esos son los que sí tienen que entregar. ¿De acuerdo? Entonces, los problemas y observaciones que dejo en la clase es pues para que vayan manejando los conceptos y salgan las dudas que pueda haber. Lo tienen que hacer, es bueno que lo hagan, pero no lo tienen que entregar. Lo que ya ponga en Classroom como tarea con fecha límite, eso se entrega y por mismo Classroom. ¿Alguna otra pregunta o duda?
De la clase no.
Y bueno, también todo el concepto esto del atlas y las cartas, al principio muy abstracto, pero les digo, ya conforme avance todo tiene más sentido, ya nunca cargamos con el atlas, inclusive en ocasiones ni siquiera con las cartas. Pero para tener algo formal se tiene que hacer esto, definir muy bien todos los conceptos de un atlas maximal, todo lo que define a una variedad. Muy bien. Bueno, entonces continuamos. Yo les aviso también por Classroom.